Okay, so let's get started with where we have left off yesterday, which was eddy viscosity models. So in a two equation model, so one example we discussed is eddy viscosity could be a function of turbulence kinetic energy and its dissipation rate, right? So in a two equation model, eddy viscosity model, one option for mu t is we can take mu t as c mu k square over epsilon, and this we have got it from the dimensional analysis. And if, of course, here the question is what is c mu, what is k? K is of course turbulence kinetic energy, but we need to see how to get this. This equation, when we derived it, it is not closed. There was a turbulence closure problem there also, and epsilon is the dissipation rate of turbulence kinetic energy. So now we'll see how to go about it. So the first thing is, of course, to look at, I'll come back to C mu later. First we'll see the K. We have an equation, an exact equation for K, so we'll proceed in that direction. Okay. So we have an exact equation, or I can write modeling turbulence kinetic energy. Okay. So we have an exact equation for K, or your turbulence kinetic energy, which is we have dou K by dou T plus, this is a transport equation, of course, Uj dou K by dou Xj equal to, we have on the right hand side the three terms, the diffusion rate, production rate and the dissipation rate. So dou by dou Xj, the diffusion rate, the three terms, which is the pressure diffusion rate, P prime Ui prime delta Ij minus half Ui prime Uj prime plus we have the diffusion rate due to viscosity, which is dou K by dou Xj. Okay, the exact equation I am writing, and then the production rate, which is minus Ui prime Uj prime over bar dou Ui over bar by dou Xj minus the dissipation rate, which is mu dou Ui prime by dou Xj dou Ui prime by dou Xj, the square term. Okay, so this is your dissipation rate. So I can symbolically write this as, this is dk here, the diffusion rate term for the turbulence kinetic energy, and this is your pk, this is epsilon. Symbolically one can write like this, the transport equation, the three particular terms. So the left hand side I don't have to do any modeling, the mean velocity is available, k is what we are computing, but the right hand side we see that there are far too many unknowns, right? So we have specifically turbulence kinetic energy. To compute turbulence kinetic energy, I have this Reynolds stresses, that is an unknown, the dissipation rate, and this correlation for the diffusion rate due to turbulence term and the pressure term. So we have additional unknowns that we have to model. So this is the exact equation here. So now we will proceed towards modeling. Okay. So for modeling, I will take up first the production rate. How do I model? So we call it, let's say, PK model, the model term. So the exact term is available, which is pk exact, right, which is minus ui prime uj prime over bar dou ui bar by dou xj. The mean strain I don't have to model, that is available. The Reynolds stresses we need to find a way. So how do I do this? So pk exact is known. So what should I do for Reynolds stresses? ui prime uj prime over bar is an unknown. It is 6 unknowns are there. Okay, so what is the modeling idea here? How do I close this particular term? Boussinesq, right? We already used Boussinesq hypothesis to close Reynolds stresses in the Rance equation. So I am going to use the same Boussinesq here. Okay, so modeling using Boussinesq hypothesis again. Alright, so I can say pk model is now essentially pk model term is equal to the minus ui prime uj prime. I am going to substitute this as your 2 nu t Sij minus 2/3 k delta ij. Okay, and of course the mean strain. This is your pk model term. So it was straightforward to use the Boussinesq hypothesis here, but you must understand that we are actually modeling the production rate or the generation rate of turbulence kinetic energy, okay, in a statistical approach. So this has a far reaching consequence by modeling the production rate. You are telling the flow system how much turbulence to be generated using the Boussinesq, and we will see later that this actually leads to errors. Okay, so there is a modeling error associated by using Boussinesq hypothesis for the production rate here. I'll come to that later. What are the issues with modeling like this? But right now the model is now closed. The 6 unknowns, this 6 unknowns here, now that has been closed using nu t, which is c mu k square by epsilon, and we are going in that direction of closing the k. So k will be computed. I will soon tell you how to get epsilon and c mu. So mu t is anyway one of the thing that it is not introducing any additional unknown here by closing pk using Boussinesq. Mu t is already there existing, and we have figured it out how to do that. Mean strain rate you have access. Turbulence kinetic energy is what we are modeling right now. So it has not introduced any additional term than what we are already discussing about. So this particular term is now taken care of. This is modeled, right? So now we look into the diffusion rates. Now coming to the diffusion rate, there are 3 different terms here. Diffusion due to the pressure, right? Pressure diffusion rate, turbulent diffusion rate, and the viscous diffusion rate. So in this is clear. There is no change in the sign. It is minus ui prime uj prime over bar is modeled as pk model. So pk is this particular term here. The pk is entire part, but what we are modeling is this closing the Reynolds stresses minus ui prime uj prime. Follow the Boussinesq. I have not changed any sign here. Okay. So now we have the diffusion rates due to 3 different terms. So here we make some modeling assumptions again in the diffusion rates. The first thing is that we look at, we take help from the data here. So we have to look at direct numerical simulation data, and then we see that which term is possible to neglect. So the viscous diffusion rate we cannot neglect because viscous effects are dominant very close to the wall. We have seen even in a turbulent boundary layer, there is a zone very close to the wall called linear sublayer where viscous terms are dominant to first order, right? Turbulence is negligible inside a turbulent boundary layer in that thin zone. So viscous effects are always dominant very close to the wall. So viscous diffusion rate we cannot let it go. But when we compare all these three terms, viscous diffusion rate, turbulent diffusion rate and pressure diffusion rate in some canonical flows like a smooth wall boundary layer or a smooth pipe flow or a smooth plane quad flow and so on, we see that pressure diffusion rate is much smaller compared to a turbulent and a viscous diffusion rate. So, viscous diffusion rate dominates very close to the wall, turbulent diffusion rate dominates away from the wall, and the pressure diffusion rate is minimal, and it is also a complicated term to model. So, the modeling argument is we take to model this dk model. The first modeling argument is upon comparing the three diffusion rates, the pressure diffusion rate okay, this is your P prime UI prime bar term, P prime, this particular term, pressure diffusion rate is small compared to the pressure diffusion rate is small in some canonical flows. Example, smooth wall, turbulent boundary layers, pipe flows, wherever you have a smooth wall turbulent boundary layer like pipe flow, channel flows, quad flows or a flat plate boundary layer. In that flow, this is from the DNS data we can see this, okay. Upon comparing this, small in, this is of course coming from, information is coming from the DNS data. From the budgets that I discussed once, we look at all the terms and see which is big and small in a particular flow, okay. So, this particular term is now small, and therefore, for modeling sake we are omitting that term. At least in this kind of flows it is omitted, but this modeling term, omitting it is a, what to say, if you take any general purpose flow, because the models are used for all kinds of flows, we will see that this is not a small term. I can show you the data, for example, here. So, this is from our own in-house DNS data of the same turbulent plane quad flow that you are used to see the data that I am showing. The only thing is I have introduced now what is called roughness. So, I have the same problem as I discussed before. So, this plate was moving in this direction, right, U wall, and this was fixed like before. The only difference is now I have introduced some obstructions here at some separations, small distance. So, I am putting small ribs. This is typically used in heat transfer application. So, I am putting some small rib roughness, okay. This is just to illustrate that all I did is I changed the flow problem only minimally, just introduced little bit of roughness close to the wall, and you see from the data here, this is the roughness element here, the rib roughness. I am showing only a single pitch, that is the gap between only this part, only this distance I am showing here in this part along the x direction, okay. This is along your x direction and this is along your wall normal direction, okay. So, this particular. So, as you see, this is wall to wall, this is your turbulent diffusion rate, viscous diffusion rate and the pressure diffusion rate. So, if I come close to the wall, let us say the values are going, let us say the maximum is like 0.06 for a turbulent diffusion rate, and they are pretty large actually compared to the viscous term. Viscous term is even much more smaller. And I did mention this idea of this inertial sublayer or the buffer layer, linear sublayer. I think somebody asked this question, is it universal? And it's not, because the moment you disturb the inner layer, all this linear sublayer or the buffer layer vanish, because you are disturbing the flow by introducing a small flow separation or a vortex generator here. This small roughness acts like a vortex generator, disturbing the near wall boundary layer. And so the viscous effects, at least now you see, it's an order of magnitude smaller, 10 times smaller than turbulent diffusion rate. You are able to see these numbers on the screen. So it's, let's say, near to the rib I have 0.06 and it is 0.001 in the viscous, 10 times smaller. But if you look at the pressure diffusion rate, it's about 0.04, 02 and so on, same order of magnitude as turbulent. Okay, so those who are experts in aerodynamics, you would know this bluff element introduces what is called a form drag or pressure drag, right? So the pressure effects are big in this type of regions close to this box here. So obviously the pressure diffusion rate, transport due to pressure field, is now comparable to turbulent diffusion rate, and the viscous effect is minimal here. So the modeling assumption here will go wrong. So if you are going to use the model blindly without knowing its assumptions, obviously you will see error and you will not know where you have gone wrong. So that's why I am showing you the data, that the model assumption has been done for simple canonical flows where a smooth wall turbulent boundary layer is considered. Okay, based on that only we are building the entire modeling approach, right? So this modeling argument, that pressure diffusion rate is small and therefore this is omitted, right? So modeling argument is, upon comparing the three, pressure diffusion is small, so therefore omitted. Okay, but this is not true for general purpose flow problems where this term can go big. But anyway, to proceed further, now we have this turbulent and the viscous term. Viscous term I don't have to model because K you are computing and viscosity is known. Okay, no need to model this particular term, right? No modeling required. Because K and nu are what is being known or computed here. Only the turbulent diffusion rate needs to be modeled. For that we are going to use what is called a gradient diffusion hypothesis. Okay. So to model turbulent diffusion rate, which is basically you have ui prime, uj prime over bar, right, half of it. This is your turbulent diffusion rate term here. Okay. So the pk, yeah, this particular term was entire. Fine. Yes, to do this we use what is called a gradient diffusion hypothesis. This phenomena is known to some of you, no? Those who have taken heat transfer courses, they would have learned this, what is a gradient diffusion hypothesis. For example, if you have high temperature zone and a low temperature zone, so the flux will go from a high temperature zone to a low temperature zone, a gradient diffusion. Okay, so similarly we take similar analogy that now the flux of turbulence will move from a high turbulence zone to a low turbulence zone. This is because it's a transport term, right? Diffusion is nothing but transport and turbulence itself is transporting. So we use this gradient diffusion hypothesis. So what it does is, basically, if you have a high or I can write it here, if you have a high turbulence kinetic energy zone to a low turbulence kinetic energy zone. So there will be transport in this particular direction, or you can say the gradient, transport from high TKE to a low TKE zone, and this we have seen analogous to your Fourier's law of conduction, right? Analogous Fourier's law of heat conduction, where you have your flux, let's say Qx, the x direction, you use the thermal conductivity and the gradient of your temperature, right? So similar to that, we construct the TK, or sorry, the model for the turbulence diffusion rate. So we can say similarly, this particular model, this is the exact term here, this is the exact. Similarly, a model for this term would be, this entire exact term is replaced by, for example, minus nu t by sigma k. We will see what sigma k is here, another constant being introduced, and of course the gradient dou k by dou x j. Okay, this is the model term here. So now together I have, this is exactly constructed similar to your Fourier's law of heat conduction. So mu k is, sigma k is an unknown, sigma k, a model constant. Nu t we have access to, c mu k square by epsilon, k you are computing. So now if I introduce this into the dk model, so essentially this is omitted, right? So this is neglected or omitted, this no modeling is required, and only for this term we have now constructed a model, minus nu t by sigma k, dou k by dou xj. So that is for the entire term here. So it's minus of minus, it becomes positive. So essentially it becomes dou by dou xj of nu plus nu t times dou k by dou xj. So this particular term, exact one, is only this part. Okay, here the pk1 was this entire thing, pk. Okay, this pk, and the dk is only, or the turbulent diffusion rate is only half of this term. So now I have the dk model, therefore is constructed as, therefore dk model term entirely looks like you have dou by dou xj of nu plus nu t by sigma k dou k by dou xj. The viscous and the turbulent diffusion rate are considered, omitting the pressure diffusion rate. So this is the model for the diffusion. So I have the modeling ready for the diffusion rate, where it is, we are falling back on viscosity and eddy viscosity to help us to decide how much turbulence kinetic energy is being transported. Okay, and of course eddy viscosity depends on Boussinesq, it depends on other flow quantities as well as some turbulence quantities. It depends on the k itself again. So you can see the coupling that is involved. You have to look at this equation carefully again, you will see the coupling, right? So the transport of turbulence kinetic energy depends on mu t, and to compute mu t you need k. and the transport of k requires nu t. So there is a coupling. So the coupled system of equations is what you are going to solve, right? So you need a robust equation which will be numerically stable, otherwise the code will crash. Okay. So at least diffusion rates are done, production rates are done, only the dissipation rate is now to be modeled, epsilon. Epsilon, we know that this is 9 unknowns here. Right. So it is a positive term, this entire part here, right. This is your epsilon, minus epsilon. So in the eddy viscosity models, epsilon is not modeled based on considering each of these terms. These are far too many unknowns that you can, it is a correlation term, 9 correlation terms. So we don't proceed in that direction of coming with an argument for that. And one can say, why not solve a transport equation? That's why I told this is a 2 equation model, 2 equation implying 2 transport equation. What is the second transport equation apart from k? Epsilon. So we can solve a transport equation for epsilon. Okay.